So, as I've said a few times now, we spent a lot of time with regular languages. We spent a medium amount of time with context-free languages relative to the size of lot. It's very medium, even small. And now we're leaving context-free languages and we're moving into kind of the everything else category. And the good news is, having seen stuff in regular languages to great detail and then in context-free languages a little bit less detail, this next step we'll also do in a little bit less detail, but it's going to be a little bit more challenging, a little bit more interesting. So let's very quickly review where we came from and where we're going. We started with regular languages, and of course remember that a language, we're always just talking about a set of strings, right? And we represented our regular languages as regular expressions. We found regular grammars that could generate our regular languages, and we had a couple of kind of things that I sometimes called computers. I mean, they are computers, they're very simple computers. Our DFAs and NFAs, which we could use to kind of run a program almost to check, right? Is this string in my language? So that was the regular language, and we have this kind of, you know, we could call this a Venn diagram that has the set of regular languages in there, because as we know, there's some languages that are not regular. So continuing on with our Venn diagrams, we've got the regular languages, but then we've got some languages in here that are not regular, right? And to prove that, there was the pumping lemma for regular languages, which we could use to do a proof by contradiction to prove that there are actually some languages that are not regular, because the pumping lemma was a property that told us something about regular languages, and if we found a language didn't have that property, then it had to be out here, right? It had to be not a regular language. And of course, we called the languages that are in this region the context-free languages. This is a superset of the regular languages. Again, you know, think of this as a Venn diagram, right? And all of our regular languages are definitely inside context-free, but there are some languages that are context-free that are not regular, right? So a language that's right here, for example, context-free, not regular. A language that's right here, regular and context-free. And then we talked about how to generate context-free languages using a context-free grammar. And we also talked about a single machine, our PDA, which again is a kind of simplistic computer, right? That could tell you whether a language was in fact, whether a string was in my language, right? So the PDA tells me, is this string in my language? Right? And the interesting difference about the PDA from our NFAs and DFAs was we had a little bit of memory, right? It wasn't a great quality of memory because it was a stack, and we could only kind of see one thing at a time that was on the stack, but still, it was amazing because, you know, if we had a language like A to the N, B to the N, such that N is a natural number, right? Our favorite language that is not regular but is context-free, we could look at strings in this language using a PDA to determine whether, they were in the language, right? Whereas you just can't do that with an NFA or a DFA. So that's interesting and cool. That was our context-free languages. And punchline, you kind of knew this was coming. I probably said it in an earlier slide in this lecture, right? There are languages that are not context-free, right? And this is sort of the everything else. Perhaps this outer circle in our Venn diagram really shouldn't be a circle, but it should just be the universe of everything else, right? But we've got, you know, here's a language right here that is not context-free and not regular, as opposed to a language in here which is both regular and context-free, right? Or something in here, context-free, not regular, but also kind of in this everything else category too. Now, just like we proved that some languages are not regular by using something we knew about regular languages, right? The pumping lemma, which now we're going to call the pumping lemma for regular languages. We used to just call it the pumping lemma. There is, in fact, a pumping lemma for context-free languages that will tell us something about context-free languages. And if we have a language and we assume it's context-free and we do a proof very similar to the proof for to prove that a language wasn't regular, we can show the language is not context-free if it doesn't meet certain criteria. So just as a reminder, here's our pumping lemma that we used for regular languages, and now we're going to call this the pumping lemma for regular languages. And we said, let L be an infinite regular language. And of course, it has to be infinite, right? If you have a finite language, remember, this is really important. All finite languages are regular, right? Because if you think about it, if it's finite, then it just has a finite set of strings. Let's suppose there's 10,000 strings, right? And the first string is AB, and the second string is BCDA, and the third string is QED, and whatever. You can represent that using a regular expression that just has 10,000 different things in there. Did I say it was 10,000? A set of 10,000 things? So all finite languages are regular. Okay? And what we really care about is infinite languages. We're looking to try and prove something is not regular. So it we say, suppose we have an infinite regular language, and then we said there exists some value m, so that if we have any string that's in the language where the length of the string is at least m characters long, then we can split S into this subpieces x, y, and z. Remember all this? Where we said y is definitely not the empty string, and the length of the xy part of this substring is less than or equal to m, and we can pump it, right? And how do we pump it? We can take 0 or 1 or 2 or 3 copies of y, and that will still be in our language, right? So this was the pumping lemma for regular languages. And here's the pumping lemma for context-free languages. It's written in such a way that you can kind of see the differences here, right? So of course our language has to be an infinite context-free language, because if it weren't infinite, we know for sure it would be just regular, which means it's context-free. Now, instead of splitting S into XYZ, we are now splitting S into more pieces, right? U, V, W, X, Y. And this kind of makes sense because before, with the pumping lemma, we could pick any one piece and pump it, and our string would stay normal, or would stay regular, right? Now what we're going to do, I mean, here's again, the punchline here, is that instead of just pumping one piece, we're going to be able to pump two. So, and this should make sense to you, right? Because this is with our stack that we have for our PDA, for example. You can kind of match two pieces of a string and pump them infinitely long, and it will still be context-free. It'll still be something that your PDA could recognize, right? And so if you look at this page here, the pumping lemma for context-free languages very, very similar to the pumping lemma for regular languages, except we're going to split our language into U, V, W, X, Y, right? And so our string, we're splitting our string into U, V, W, X, Y, right? So, and the important thing is the Vx part is not lambda, or the length of the Vx part squished together is greater than or equal to 1, right? So this is very similar to this rule here. And if we take the VWX part, so that's this middle part, ignoring you know, the stuff at the very beginning and the stuff at the very end, that has to be less than or equal to m, right? Whereas before, the length of that, whereas before we had the length of xy had to be less than or equal to m. And then there's this last piece that says it can be pumped. Now, at this point in the class, I always get questions, do I need to know this? Am I going to have to be able to prove that languages are not context-free? And what I'm going to say is, for this particular topic, you need to understand the basic idea, but I'm not going to make you prove that languages are context-free. So what's my basic idea here? You need to understand that the pumping lemma for context-free languages, just like the pumping lemma for regular languages, tells us something about context-free languages. In particular, it tells us if you have an infinite context-free language, then any string that you pick whose length is greater than some integer m, greater than or equal to some integer m, right? And m is some value we don't know, but we know it exists. Then you can split that string into 5 parts squished together so that the v or x, right, so these two pieces are, or both of them are not lambda. One of these two pieces is not lambda. And if you take this VWX piece all squished together, its length is at most m. And we can pump these v and x pieces simultaneously to get more strings in the language, right? And the point of this is we use these facts to prove that a language is not context-free when we're doing a proof by contradiction. Okay, so this is what you need to know. How do you remember it? Well, you know that you need to know the context-free, the pumping lemma for regular languages, right, which is this stuff that's crossed out over here, right? And the pumping lemma for context-free languages is incredibly similar. Regular languages split into 3 parts. Context-free languages split into 5 parts. Okay, I don't know why they started at U, but they did. Too bad, right? And the part that we pump is kind of the every other part here, right? So we're pumping the V and the X. One of those pieces or both can't be lambda, right? And the whole triple piece here has to be less than m or equal to m, less than or equal to m, just like this xy part was less than or equal to m. And then we can pump, and we're pumping the v and the x parts. So you need to know these facts, but I'm not going to make you do an entire proof using the pumping lemma for context-free languages. I still feel free to do the one that make you do proofs for to prove that the language isn't regular. But for now, I'm going to keep going and talking about one of the most fun things in here, which is talking about a computer for non-context-free languages, right? A machine, some sort of a machine. And remember, I mean, we've already said, okay, we have a machine that will recognize regular languages, right? We have 2, actually, a DFA and an NFA. Those are, you know, they're kind of small computers that recognize regular languages. You give them a string, you give them, and it will tell you this string is in the language or this string is not in the language. And of course we continued and we came up with a new kind of machine for context-free languages, which was the PDA. And of course anything that you can recognize with a DFA or an NFA, you can also recognize with a PDA, but the PDA was a little bit more powerful than the DFA and the NFA, and we got that power from the stack. Right? We added a stack to our NFA, and suddenly we just had so much more power. We had a little bit of memory, right? And memory always helps. So the machine for everything in here, which is actually anything you can program, this really is a machine for everything else, is called a Turing machine. And like I said, the Turing machine really is for anything else, everything else. Anything that you can program using a Turing machine. It will be a major pain to do it on a Turing machine. And I have here, you know, your input-output isn't going to be the same because a Turing machine really can only write symbols. It can't give you pictures. It can't give you sounds. But of course, we know that you could represent anything in binary. So we'll assume that whatever the Turing machine outputs, we could translate that into a picture, or we could take a picture, translate it into binary representation of that picture, and put it into our Turing machine as input. So really, the Turing machine is equivalent to the PC, the Linux machine, the Mac on your desk. Okay? We are now actually going to talk about a computer that is a model for every other kind of computer, right? And here's where it gets fun, because remember, I said that there are programs that cannot be written. Right? And if a Turing machine is equivalent to any other computer, and we're not going to prove that, but trust me on it, then if we can prove that a program can't be written on a Turing machine, then we can prove that program can't be written anywhere. And we are very, very close to proving that there's a program that cannot be written. That's 2 lectures from now, so get ready. Very exciting. It really is. It's good. It's cool. You will like the proof. It will be you may have to watch the video a couple times because it's going to be one of those what did I just see proofs, but it's a good proof.